Here we are doing limits and derivatives. I decided to stick these together because neither topic is too terribly difficult, whereas integration definitely deserves its own day. Plus, limits, right? Limit cares about what happens as I approach. It doesn't matter what actually happens at the value. A limit just says, hey, on the left side it approaches this amount, on the right side it approaches this amount, and we hope those two amounts match to then say the general limit exists. We can also do limits as it approaches infinity, as something leaves the page forever and ever. Does it go to a specific number or does it just approach infinity? Positive or negative. Those are the ideas kind of talked about here at the top. It doesn't matter if the actual value exists, right? At this place, when I plug in 2, it will have a hole in the graph. It simply won't exist, but I can tell you what it does as it gets infinitely close to 2. Let's do some examples. That's mainly what today is. An example fast front side limits backside derivative. Here we go. The simplest and easiest way to always evaluate a limit is just to plug it in, right? This would be 2 times 3 squared minus 5, I would get 13. Right? If a limit is that simple and it's that easy, it's that nice. But it's not really usually that simple and that easy. So let's keep going. We can look at factoring and rationalizing as we learned in our algebra practice. The fact that I could factor this using a difference of squares. And that would help me simplify here to say that the original statement is equivalent to this statement. And then again, just as we did last time, finish with some direct substitution. How about some rationalizing? I can rationalize this numerator and hope that it somehow fixes my denominator. I know this top becomes a difference of squares, and I would get x plus 1 minus 1. I know my denominator would turn into this. Notice, I'm not going to drop these parentheses. That was a yucky parentheses. I'm not going to drop those parentheses. I'm just going to leave them because I'm hoping to factor out the x, which does end up happening, right? This plus 1 minus 1 becomes 0. This x over x becomes 1. And so this limit is then equal to this. Which I can then evaluate at 0 to get 1/2. You could have also used L'Hopital's there, but it's a little bit messier. I don't know, to me, both are good. That's why we learned this skill too, because it's useful for evaluating limits, even if we don't want them to be yucky limits. Here we are. I can use L'Hopital's on this one. I know Ms. Taylor just taught you guys to memorize this one because it shows up often, but I see a 0 over a 0. Or infinity over infinity, therefore L'Hopital's applies. I'm not making you do the prompt, I'm just going to say this. And I really think it's important to write this statement. We didn't do it as much in AB, but just to say, hey, the limit of the function divided by the function is equal to the limit of the derivative divided by the derivative. And now, once again, that's equal to cosine 0, which I know is equal to 1. Send it. Onwards. The squeeze theorem. You see this most often with signs. You see this most often with things that are multiplying. And I just set it up as one big inequality and slap on some limits at the end. This is to say that, hey, sine as a function, as we learned, is always between 1 and -1. Well, therefore, negative x is always less than or equal to x. See, I just multiply all three sides by x. Now I slap on the limit. Going to be tight on space, but we're going to make it. Right? I know these sides both go to 0 very clearly. Since it's greater than or equal to 1 and less than or equal to the other, therefore, this limit must equal 0. And notice, I threw in this sign 1 over x at the start. The sign of anything is between -1 and 1. And notice, I'm not saying the value is equal to 0. I'm not saying when I plug in 0 and 0, I get 0. I'm saying, hey, from the left-hand side and the right-hand side, both of them approach 0. So I know what the graph approaches. I know what the limit approaches. All right, leading term, most dominant term. This has to do with horizontal asymptotes and some infinites limits. This first one, again, we just need to remember, I forgot to change this one over. This should be any base to the power x. Any base to the power x, right? Because the amount of multiplications will be huge. So here we are. In this one, I see that I have x as a base versus x as a power, and I know x as a power will be the dominant term. That means my numerator is going to outpace my denominator. That means I know this limit is going to be equal to infinity, just because of dominance. Here in this one, I look for the dominating terms. It's going to compare these two. Well, this fraction just reduces to 4 over 2, which is just 2. So completely outside of what x is equal to, I should get a 2. Even looking up here at signs, I'd get a negative. I'd get a negative. So I'm not even worried about, oh, what if it becomes negative big over negative small or something like that. My signs are all going to work out there. And here, yeah, ln x, I don't care about this guy. It's not dominant at all. It's less than x to a power. This is going to be tiny. Not worried about this. Again, not the dominant term. I'm comparing these and thinking, well, the denominator is greater. Therefore, my limit is going to equal 0. That quick. When you know that scale of dominance, you can do those infinite limits fairly easily, especially when you're dealing with these rational functions one over another. And last but not least, continuity. The whole kind of purpose of limits, we can't have a derivative if something is not continuous. We can't take an integral if something's not continuous. And we can't prove something continuous without limits. And that's why we have limits. Again, to read this sentence for you, look at this double f. It's not an accident. X is only continuous at a. F of x is only continuous at a if and only if, that's what this guy stands for, if and only if the left-hand limit is equal to the right-hand limit is equal to the function's value at a. And so that's what you'll see me here when I evaluate this left-hand limit. We get the same as when I evaluate the right-hand limit is actually the same as when I just plug in 1 to that upper term. And all of those are just equal to 1. Therefore, this thing is continuous. Over here, I know these things are not going to be continuous because I'm dividing by 0. So even if I can use some limit tricks to show that my function's approaching, I know the value at will never quite exist. So it's not going to be continuous. I'll tell you that from the start. And thankfully, I built these notes to bake in, hey, we did this example earlier with L'Hopital's and we found the answer to be 1. Hey, we did this answer earlier with rationalizing and we got the answer to be 1/2. Hey, the limit of 0 is 0. Notice that's a vector function. We haven't dealt with these much. We'll deal with them plenty this year. Just understand that x, y, and z are all kind of moving independently, dependent on t. So they're a little bit codependent. The language there is a little bit fuzzy. But just understand, I treat them as individual functions on their own, evaluating whatever t is. And we'll see another one of those on the back too, don't worry. Let's start up here at the top, derivatives, right? The derivative is just the idea of rise over run. These are my function outputs divided by my function inputs, and I have an infinitesimally small change. So it's just the smallest change in run compared to the smallest change in rise along this big, huge curve that's happening. And that smallest change in run and rise will give me that tangent line. And again, as we move into 3D functions and spirals and surfaces, this tangential idea where it just barely touches the smallest amount of run change compared to the smallest amount of rise change will always result in some kind of slope. All right, here I have my derivative rules, right? We're not going to usually use this fundamental definition of derivatives as much as I would love to. Generally, things fall into these camps: power rule, product rule, quotient rule, chain rule, and even a couple of good reminders of these things over here, right? Some trig, some natural log, e to the x, a little tangent inverse. All right, just two quick ones that I want to do over here, some derivatives. Now I chose particularly tricky ones just because I only had the space to do two. So let's do two. I see this as some division, so it will be a quotient rule. The quotient rule goes bottom d top minus top d bottom over bottom squared. So I'll go bottom d top, there's my derivative of the top, times the thing on the bottom, minus top d bottom. The derivative of this thing is not very kind, right? I have a chain rule here, 2x. And this is going to get power ruled. A square root's a 1/2, so it gets power ruled down to a negative 1/2. But thankfully, my denominator doesn't really change. It just gets squared. And from there, I would algebra and simplify for the sake of space and time. I trust that you'll be able to do that. I would get this to the 3/2. Some funny things would happen with these x squared plus 1s and combining like terms, but it is a great example. Here we go. Over here, I do have a product rule. This would be derivative of the first times the second, then derivative of the second times the first, right? Cool. Product rule. Well, even inside that product rule here, I have a chain. That'd be derivative of the inside times the derivative of the outside. So when I do the derivative of this first thing, I get the 3x squared as derivative of the inside times derivative of the outside, cosine x cubed. Don't forget, I have to multiply it by the other thing. How ugly. And then over here, I take the derivative of the second, just times the first unchanged. And that's a nice derivative for us. And if you really challenge yourself on the algebra, that's what that quotient rule would eventually simplify down to. I don't think taking out a 2x makes it any nicer, but I did separate it because I saw I could kind of combine here and kind of combine there, but to bring it all under one house would not do a whole lot. All right, that tangent line, as much as I get the slope from taking the derivative, if I have a point and a slope, I have the equation of a line. And that really comes from the idea that slope is equal to a change in y over a change in x. And I just multiply both sides by that denominator in case nobody's ever derived that point slope formula. That's all that thing is. So I take my quick power rule derivative over here. I evaluate it at x equals 1 as the question asks me to do. My slope is now 1, but I also need a coordinate at 1, so plug 1 in. I'll get 1 minus 2 plus 5. That means my slope here is just actually, or my point here is going to be 1 comma 4. And so I put those things together. Y minus 4 equals 1 times x minus 1. Nice clean answer there for us. And again, this format just comes from here where this is my m. And I leave x and y generic because now it shows me the whole line instead of just the slope at one line because it's a consistent slope. That's some yapping. Here we go. Tangent vector over here. All right, tangent vector just says, hey, if I have a vector, I can take a derivative, and if my vector points here, I would find that kind of tangent vector at that point. And we'll see a lot of this in our motion unit, which comes up in chapter 13. We will deal a ton with this concept of a tangent vector, a normal vector, a binormal vector, and working within that world. But this is just, again, a function defined by t. The x is going to just stay at 1, so I'm along that plane of x equals 1. My cosine, my y value, is constantly oscillating. My z, my sine, is constantly oscillating, so it'll be kind of this wavy thing along that plane, x equals 1. All I have to do is take my derivative, r prime. There's no change in x. Make those hard brackets, and then plug in my pi over 4 to wrap this thing up. So that's my general rate of change along the whole curve as defined here. This is the rate of change in each direction. So this vector pointing at that moment would be tangent to the original RT curve at that moment, t equals pi over 4. Down here, implicit is not everybody's favorite, but it is useful, and we see it all throughout this class. We kind of technically just did it there. But what you see here is that I need to find a derivative with respect to t. Well, this isn't in terms of t, and that's not in terms of t, and that's not in terms of t. respect to t. I still get the 2x because that's how x changes, but I get a dx dt. You guys might think of this as parametric from BC, but I get all these things. And now it just says find dy dt. So just solve for this piece. With a little bit of algebra, I'm sure you can see how this isn't too tricky. And then divide it out. Put my final answer over here. And I'm sure I could simplify the 2's, but we got a nice answer over here. Negative 2x dx dt over 2y. So the change in y is based on the change of x, which are both based on the change in t. All right, here we are. Let's do some applications here at the end. A nice question to wrap us up, but don't get too excited. A 13-foot ladder is resting on this wall, and it's sliding down the wall. My height is constantly decreasing. That means my base is constantly kicking out. So my height is decreasing, my base is increasing, and it says how fast is that base moving when the height is 5 feet. When the height is 5 feet, I trust you to do Pythagorean theorem and get this as 12. I know this thing is sliding down the wall at negative 2 feet per second. Don't forget, I should probably label these A, B, C, because what's the one formula that relates them all? A squared plus B squared equals C squared. And the thing I need to find, how fast is the base moving? That's the change in base with respect to time. So when I take this derivative, 2a dA dt plus 2b dB dt equals 2c dc dt. And then I can plug in all my relevant information. Like I know 2a is 2 times 5, dA dt is negative 2, 2b is 2 times 12. I don't know that dB dt. 2c is 2 times 13, but the length of my ladder is never changing, so that just becomes a 0. I trust in you to finish out these algebra steps, and I believe in you to get the same answer as me at 5/3 feet per second. Or 1.6 repeated, right? Last but not least, just a question to give you and let you kind of chew on. A differential equation. That means what I see here is the second derivative of some function plus the first derivative of some function gives me 4e to the x. And I'll just challenge you to figure that out. You need to tell me, hey, what is y equal to, such that when I take y prime plus y double prime, I would somehow get 4e to the x. I'm not giving you that answer, but I believe in you to go figure this thing out. Happy derivatives and limits.